The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. The late Princeton mathematician Eugene Wigner. Mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere, like that of sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure and capable of a stern perfection such as only the greatest art can show. The true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as in poetry. Bertrand Russell. Bottomless wonders spring from simple rules, which are repeated without end. Benoit Mandelbrot. None of these men believed in the God of the Bible, yet they all recognized the wonder, simplicity, depths, and beauty of mathematics. Their testimonies about mathematics confirm the truth of Scripture, namely that we can discern and rightly understand God's invisible attributes through what He has created. Mathematics is not a physical thing like stars or planets or a cup of coffee, yet it pervades the entire universe. Numbers, equations, calculations, sums, quantities are all the warp and woof of the fabric of space and time. We can understand everything from the most distant galaxy to the tiniest components of the atom using mathematics. As the 17th century astronomer Galileo once said, quote, "Mathematics is the language in which God has written the universe," end quote. Our guest on the next 2 episodes of Good Heavens is astronomer and author Dr. Jason Lisle, who talks with us about the late 20th century discovery of an entirely unknown universe, a purely mathematical universe filled with fractals. It is called the Mandelbrot set, developed in part by an IBM computer engineer, Benoit Mandelbrot, in 1980, from previous work in 1978 by Robert W. Brooks and Peter Metelsky. Supercomputer calculations of a simple equation revealed unending patterns of wonder, design, and beauty, the likes of which have never finally been explained by a purely naturalistic worldview. The laws of the universe are expressed in mathematics. As cosmologist Alexander Vilenkin wonders, quote, "If the medium of mathematics is the mind, does this mean that mind should predate the universe?" End quote. Yes, the mind of God Himself does indeed predate the universe. The Mandelbrot set is not the invention of man, not a computer glitch, not an accident of nature, but rather designs and patterns created by and through Christ Jesus our Lord, reflecting His infinite wisdom, His infinite holiness, His infinite love, mercy, grace, and creativity for us to discover and enjoy and bring Him glory. So come and see the Mandelbrot set on this episode of Good Heavens. Dr. Lisle, it's wonderful to have you here on Good Heavens. Thank you for joining us today. It's fantastic to have you. You have a new book out that we're going to be talking about today. A wonderful book for anybody. I mean, you have written this. It's about math, but it's about beauty and design and truth. It's called Fractals, The Secret Code of Creation. I just got this. It's a beautiful book. It is a beautiful book. Congratulations on a visually stunning book, Dr. Lisle. Fantastic. And so what we're looking at is not the designs in this book are recently discovered. They're not man-made creations of a modern-day Picasso or something. We're looking at mathematical patterns. So why don't you just jump in and tell us, like, how can math give us beauty? What is going on here, Dr. Lisle?
Yeah, well, it's my conviction as a Christian that God's mind is responsible for mathematics, and God's mind is responsible for the beauty we see in the physical world. And so it doesn't surprise me to find beauty in mathematics as well. And by the way, I should point out too that you don't have to know anything about mathematics to read this book and enjoy it.
That's absolutely true.
If you understand 2 + 2 = 4, that's all you need.
Right.
Because basic addition and multiplication. You don't have to have had calculus or anything like that.
Yeah.
And really only the first chapter in the book goes into just a little bit of mathematical detail so you can understand what it is that the rest of the book is about. And then the rest of the book is exploring these beautiful shapes that have been built into numbers by, I would argue, the creator of numbers. And as revealed when we explored mathematical relationships between them. This all started really if we really wanted to back it up to 1978, that would be it. But really the 1980s is when we started discovering these things, because mathematicians were very interested in recursive algorithms. And a recursive algorithm is something that you do over and over again, where you take the output of it, whatever it is, a number, and you put that back in as the new input, and you get another output, and you put it back in, and you do it, you keep doing it, keep doing it, keep doing it, keep doing it. And one of the things that was very surprising to mathematicians is that in some of these algorithms, if you change the input by just a little bit, it results in an enormous change in the sequence as you run it through many, many times. Sometimes that sequence will remain small, other times it'll get really, really big. And just a very small change in the initial condition can change that. And today we refer to that as chaos.
Yeah.
And it has a specific meaning in mathematics. It doesn't just mean sort of messiness. It means that a very small change in the initial conditions can result in a huge change in the outcome. And in particular, one set that people were looking into, it's called the Mandelbrot set. It's a set of numbers that are defined by this little recursive algorithm. And the algorithm is very simple. It's z squared plus c. That's it, z squared plus c. So z is one number, c is a different number. C is the number you're checking to see if it belongs to this set. Z is a number that is initially 0. And so initially you have 0 squared plus whatever number you're checking, c. Maybe it's the number 1. You're checking to see if the number 1 belongs to the Mandelbrot set. So you have 0 squared plus 1. That's your new number. Well, 0 plus 1 is 1. You take that, you put it back in. That's the new value of z. So z squared, 1 squared is 1, plus 1 is 2. Put it back in. 2 squared, that'd be 4, plus 1 is 5. Put it back in. 5 squared, 25 plus 1, 26. You put it back in, and so on. And you can see what's happening there is the sequence gets really, really big. 1, 2, 5, etc. And so that number c does not belong to the Mandelbrot set if that sequence gets big. And you'll find for other numbers like 0 or -1, the sequence remains small. And you can see why this began to flourish in the 1980s, because it's tedious for human beings to run
to do all that calculating, right?
Yeah. Even if you have a calculator, it's a little tricky. But it was in the 1980s that computers were starting to get really, really fast, to the point where they could run these calculations very quickly for many different numbers. And then it occurred to somebody to make a map to see which numbers belong to this set. And what they did was they plotted the so-called real numbers on the x-axis and the so-called imaginary numbers on the y-axis.
Mm-hmm.
Imaginary numbers are numbers that when you square them, you get a negative.
Okay.
So I squared equals -1. And that's kind of weird, because
Yeah,
imaginary numbers are not positive, or they're not negative, but they're not 0.
Right.
And so you can think of them as being along a different axis. And those are well studied, and it's real simple. You just need to remember that whenever you take an imaginary number and you square it, you get a negative. It's that simple. And I hate the terminology, because imaginary makes you think they're not. They don't exist.
Right.
They do exist.
Right.
But anyway, when people took and ran the numbers through the computer to make a map of which numbers belonged to the Mandelbrot set, they got a really interesting shape. It looks kind of like a heart-shaped structure with circles growing off of it. And nobody was expecting that, because it's such a simple little formula, z squared plus c. You think, well, if you run the numbers to see which belong, maybe you get a circle or something. No, you get this incredibly complicated shape. Then the mathematician and computer programmer Benoit Mandelbrot, who was working at IBM at the time, he started assigning color values to if the sequence of z gets big really fast, he'd give it a bright color. And if it gets big slow, you give it a dark color, and that colors the exterior of the map. And it turned out to be incredibly beautiful. And what was even more amazing is when you zoom in on this shape, and all it is a map of which numbers belong to this little formula.
Mm-hmm.
When you zoom in on it, it gets more complex and prettier, and some of the shapes are remarkable. They're just beautiful.
Yeah.
And you're thinking, well, this is, somebody put a lot of thought into this. And I would say, yeah, but it wasn't a human being. This is built into numbers.
Right. It's
so
phenomenal.
The book is really about exploring this shape. The first chapter tells you how we discovered the shape, and the rest of the book is just having fun exploring the shape. So really not much math after chapter 1. The rest of it's just let's look at the shape and see what's in there and what does it all mean.
Yeah, and as I'm going through this book, I'm like, this looks just like some computer design. Well, it is a computer design, but it looks like it was intentionally designed by human beings. In this day and age of computer art and technology, we think, oh, somebody just made this. But that's not the case. You're arguing that I read a little bit of background in preparation for our chat, that Mandelbrot was a little arrogant. I mean, there's a little controversy in surrounding, hey, I did it, I discovered this, but it seems to be a collaborative effort, which really has been, I think, validated in the last 40 years that this wasn't just the creation of one intelligent computer programmer. This was a discovery. This was not something, people were arguing that this was maybe an offshoot of the computer, a byproduct of the computer or something, or there's intentional human input into this. I mean, there is in selecting variables, but the bottom line is you're arguing that these patterns in this book were not the product of human design. Is that correct?
That's right, and you're correct. Early on, people thought maybe this shape was an artifact of the way the computer program was written. It was a mistake, in other words, that if you really did this calculation manually, you wouldn't get that. Well, we now know that's false. Mathematicians have demonstrated, at least that the main features of the Mandelbrot set, the main cardioid, the main disks, and so on, those are genuine. And so in other words, if you did the same thing by hand, which would be tedious, if you ran it through by hand and colored the points, you'd get exactly the same result the computer does. It just does it fast.
Right.
And so all the computer's doing is just it's discovering which points belong to the set and making a map of the result. But it doesn't determine which points belong. Yeah. The rules of mathematics and the formula determine which points belong. And so that's something that human beings don't have any. I mean, we could pick the formula. Sure. But once you pick the formula and you run the numbers through to see which belongs, that's determined by the rules of mathematics.
You're stuck with it. Yeah, that's what it is.
Exactly.
What it is.
And the fact is, people were surprised by the resulting shape, and so that alone ought to demonstrate
it was shocking.
Something that people designed.
Yeah,
right.
It was shocking.
You wouldn't make something and then be surprised by its properties.
Right. It's like it's something like discovering this beauty. Jason, reminds me of what hit observational astronomy with the Hubble deep fields and the legacy fields that we now have from Hubble. People were absolutely stunned, speechless. Even Bob Williams, the director of Hubble, the Space Telescope Science Institute, when they uncovered the first deep field off of the Big Dipper handle, there were no words. You have thousands of galaxies in this spot of sky no bigger than the head of a pin. Wow, look at this magnificent beauty that was hidden from us for so long. But now we have the technology with Hubble and now with computers to uncover the beauty of the universe, not only galactically, but mathematically right here under our noses. Now, for some of my skeptic friends, Jason, let's just briefly take an aside before we get into this design, the beauty of the designs here that we'll show people. Let's talk a little bit philosophically about mathematics, because some will argue mathematics was, there's that ongoing debate, mathematics, was it discovered or was it invented? And so how does the Mandelbrot set help us better understand this ongoing debate between mathematics being discovered or being invented? What do you say?
Yeah, and there is a discussion of that in the book, because I would argue that no, mathematics is discovered. Great. Now, there's certain things that we get to define in terms of how we express a number, like numerals. Numerals are human invention. We can either write one like that, or there's Roman numerals, and so there's different ways to express numbers, but numbers themselves aren't something we invented. They're something that we discovered, and that is particularly the case. Well, one example of this would be the so-called irrational numbers, things like pi that have an infinite decimal expression and therefore cannot be expressed as the ratio of two integers. So they're called irrational because they can't be expressed as a ratio. Those were discovered by the Greeks. And the interesting thing about that is they hated them. The Greeks were very disturbed by the fact that these numbers existed that could not be expressed as a ratio of two integers. They hated that. It was probably the first time in history that a mathematical truth had been discovered that was not anticipated and not desired. And so obviously if mathematics was something that people invented, we wouldn't do that. We wouldn't make it in a way that's undesirable to us. But nonetheless, irrational numbers came as a logical result of the fact that, well, the Pythagorean Theorem, and in order to solve that, you need to take a square root to get if you know the legs and you want to get the hypotenuse, you have to take square root, and the square root of some integers is irrational. In fact, if it's not an integer, it's irrational. So that was something that mathematics led to that discovery, and yet it wasn't something that people wanted. And fractals are the same way in the sense that nobody was expecting to find these shapes built into the laws of mathematics. We use laws of mathematics. They're very effective. They're applicable to the universe, which is another issue we should probably get into at some point. But and that makes sense again from the Christian perspective. But no, it's not something that human beings created, because for one thing, fractals are infinite. At least the kind that we're exploring in this book, these mathematical fractals. You can zoom in on them. You can zoom in and zoom in and zoom in forever, and you'll find that they get more complex as you zoom in. You'll find baby versions of the original shape built within it, which is remarkable. But the baby versions have more complexity on their exterior. They gain additional. The basic shape's the same, but they gain additional structure to tendrils and dendrites, things like that. And that is not something that human beings can do. We can't make something that's infinite. That's beyond our capacity because we're finite. And so again, that demonstrates that this can't be a human invention. We can take credit for checking the formula. We picked the formula, but it turns out when you pick different formulas, you also can get fractal shapes. That's something else that the book explores, is what happens if you try a different formula. Do you get a fractal? And in many cases, you do, and they're infinite, and they're beautiful. And so I would argue that the beauty and complexity that's built into numbers, it's not something that human beings can take credit for because it's infinite and because it was a surprise. It was something we were not expecting.
When I saw the original structure of the shape, minus all the tendrils and details we'll get into, and this is just more of a technical observation because I love astronomy. I'm not an astronomer, but I love astronomy. The basic shape of the Mandelbrot set mapped out, that heart-shaped structure, reminded me of the structure of Lagrange points. There's a similarity there. I mean, there may be correlations there, but the point there is that there is a as you've alluded to, a connection between the mathematics we discovered and the universe that we are continually discovering is best expressed in your field of discipline through the language of mathematics. And if we invented mathematics, the naturalist is bereft of trying to explain why something we invented, tiny little creatures on a very tiny little planet, would be so efficacious in describing the enormity of the cosmos. There's no explanation for that. Why would that work? But I love your point in the book and what you say about the Greeks not liking the conclusions that the math was leading them to. This certainly does attest to the fact that we didn't make this because we'd make something that we would like, right? That's our nature. We want to make something that agrees with our conclusions. So let's just jump right into the basic structure itself, Jason. We have I'm going to put some visuals up here on the screen, so just have that in mind as you're describing these things. Let's go into what are we looking at here in the basic heart-shaped structure, the main structure of the Mandelbrot set. What exactly are we looking at?
That shape is called a cardioid. And that shape is what is produced if you take a circle, you take another circle and attach it, and you put your pencil on the outer circle and roll it around the inner circle, keeping your pencil affixed to the same point on the outer circle. That is exactly the structure that you will get.
Oh.
And so it's exactly a cardioid. And that's another thing that's been demonstrated mathematically. So that's the main feature of the Mandelbrot set, was cardioid. And then all the shapes that grow off of it that are on the perimeter are perfect circles. And they are perfect circles. There's one that's growing right off of the -1 with a radius of exactly 1/4. So I mean, we'd expect mathematical shapes, but nobody was really expecting a cardioid. And why is that? We're not rolling circles around. So how do you get that?
Yeah.
It's kind of interesting. There's math connects things that we think are very, very different, but in fact, they're very similar. That's why pi, the number pi, pops up in all kinds of things, Gaussian distributions and things that have nothing to do with a circle, because that's how it was defined, right? It's the circumference, the diameter, and so on. But so it was amazing that a cardioid should be the main shape of the Mandelbrot set. But that's what it is.
That's fantastic.
It's a perfect cardioid.
You have in the book a diagram that it reminded me of kind of what we're going back to the universe here. You have a diagram with all the different sections of the cardioid, the Mandelbrot big graphic, of different sections that sound like a description of a slice of sky with constellations or galaxy names or something like that. They're fascinating, and they're named after the things that the structures that you find within them. And so why don't we go deep into the Mandelbrot set, or have we adequately, you did explain exactly how this kind of unfolds in terms of plugging in an equation. So let's look at some of these different details in the Mandelbrot set. Let's go deep into, where do you want to go first? What are one of the structures, the more finer details that we have on this?
Let's start with the mini Mandelbrot.
Okay.
So we find that when you zoom in, one of the features, we talked about the cardioid, we talked about the circles, and then the other feature would be these, I call them dendrites or tendrils, these little wiggly lines that go off. One of them is perfectly straight, and that's the one that's on the tail of the Mandelbrot. And it goes right along the x-axis.
Okay.
So there are no imaginary numbers there. The imaginary component is 0. And if you zoom in, there's a little bump on that tail, and if you zoom in on that bump, it's a baby version of the original.
Yeah, that's fascinating. That's awesome.
It is.
Yeah.
So you see the cardioid structure, you see the circles, and it's got a line, it's got a tail growing off of it, and it's got a little bump on it. If you zoom in on that bump, it's another baby Mandelbrot set, even smaller.
That's amazing.
And it's got a bump on its tail, and so on. And you could do this forever.
Wow.
And so you keep zooming in. I in the book I show several iterations of this where you zoom in 4 or 5 times.
Just keep zooming in, and you keep finding the same little Mandelbrot creature, whatever. But to explain for our audience what you're looking at, this is a graph. You graphed it, when you're in middle school and you're doing your numbers, and you graphed the x and y coordinates. This is 2, -2, and 3, -4, and you drew a picture of your points on your graph. And that's what we're looking at here is our points on a graph drawn out infinitely by supercomputers. And so this is all pictorial graphs of mathematical points on an x and y axis, with the imaginary numbers going north and south, if you will, and the real numbers going east and west on that axis. Would you say, Jason, the imaginary numbers are in astronomy? Do people posit imaginary numbers as representative of other dimensions? Is that what we're looking at here, or is it just more simple than that?
Well, they can be used to represent a dimension other than the. You can think of the real numbers as being one-dimensional, and the imaginary numbers as being one-dimensional in a different direction, and so the two together form a two-dimensional plane. And people have thought about it that way for a very long time. It makes sense, because if you think of the real number line, and you think of positive numbers being to the right of 0, and negative numbers being to the left of 0, how would you plot a number that's not positive, not negative, and not 0? You'd have to plot it on a different axis. And so it makes sense to think of numbers as inherently two-dimensional. The real numbers on the x-axis are one-dimensional. The imaginary numbers are one-dimensional in a different dimension. And then you can plot complex numbers, which have a real component and an imaginary component as being off-axis. And that is applicable to our physical universe. The problem is our physical universe is three-dimensional, at least in terms of space. We have 3 dimensions of space. We have X, Y, and Z. But it turns out that there are certain physics problems that if one dimension doesn't matter, like maybe you're looking at fluid flowing, but it's constrained to a plane, so the fluid's flowing only in 2 dimensions, you can use complex numbers to solve what happens in terms of fluid dynamics. That's something that I've done as part of my graduate work. But you can't do it in 3 dimensions because numbers are 2-dimensional.
Yeah.
And it's kind of interesting because this is something that if we had invented numbers, we might have made them 3-dimensional, because then that would correspond to the 3 dimensions of our space.
Right.
But nope, Numbers are two-dimensional.
That's
all there is to it.
fascinating.
And people have invented concepts similar to numbers called Quaternions that'll give you two extra dimensions, and that's mentioned in the book too. I think that's an interesting discussion in and of itself.
Yeah, it really is.
So you can use numbers, real and imaginary, to solve equations when two dimensions and only two dimensions are involved.
That's fantastic. So these pictures, again, to reiterate for our audience, these pictures are graphed points on a graph. These are pictograms of mathematical solutions to this very simple z squared plus c equation. And so what you're seeing is just a continual repetition of getting an answer, putting it back into the equation, getting another answer. Now, you briefly touched on it, but let's just clarify something, that not all numbers work in the Mandelbrot set. So the Mandelbrot set is very exclusionary when it comes to what works in the equation and doesn't. Now, all numbers will work. I mean, you can plug in a number and get an answer, but not all answers that you get show up in this graph, right? So what are the numbers that work and don't work, and how does that work?
Yeah, well, the numbers that are part of the set are plotted in black. And I can tell you just from memory that 0 works. It's part of the Mandelbrot set. So is -1. So is -2, I think, is the last point on the real axis. Positive 1/4 works. Positive 1/2 does not. Positive 1/2 is not part of the Mandelbrot set. And so it is not colored black. So basically all the points, so once you get the map, and I think it's figure 1.2 in the book that shows you the overall Mandelbrot set, and it's got the coordinates, it's got the real and then the imaginary coordinates. So once you have that shape, you don't have to run the numbers through the formula. You can look at the map. The computer's done the work for you. And so you can say, okay, does 1 plus I, does that, is that part of the Mandelbrot set? Is it black? No, it's not black, so it's not part of the Mandelbrot set.
Okay.
Yeah, so but the interesting thing to me is not so much whether or not the point belongs, but rather the map itself. That was what was surprising.
Right.
I mean, it was interesting enough to talk about, whether these numbers whether this number belongs or not, and the fact that you can't just by looking at a number tell. If I give you 1/2 I, you can't in your head know if that belongs or not. You got to run it through the formula a few times. And so that's why computers were so useful in discovering which points belong. But what was more remarkable was the map itself.
Yeah.
Nobody expected it to have that kind of infinite complexity.
Now,
and the fact that when you zoom in on a portion of it, you get a baby version of the original.
Yeah.
And that's what a fractal is. A fractal is something that when you zoom in on it, you get a smaller version of the original shape, either exactly or it looks similar to the original shape.
Now you have, just kind of jumping to the end of the book, just really quickly as a question, you have examples of fractals in nature, snowflakes and flowers and galaxies and spirals and things like this. Is there any hint in the history of mathematics with which you're familiar that suggests that anything like the Mandelbrot set would even exist? Or is this really like in the last 40 years we've stumbled onto this? There's no indication, because of the necessity of the kind of computation involved. Greeks and everybody else, Pythagoras and everybody since then, nobody had any idea this existed.
Yeah, in terms of the shape of the map, that was unknown until 1978. That was the first time anybody plotted the Mandelbrot set, and even then it was a very low resolution version. It wasn't until the 1980s that we started getting more complex shapes. So this basically, in my mind, this is a new universe to discover that was unknown to our ancestors, and we can explore it now. And it's not a universe that's made of atoms; it's a universe that's made of numbers. And the cool thing is, if you have a computer or access to a computer, and most people do these days, if you're watching this podcast, you have access to a computer, and you can explore that universe yourself. Because in the book, I've actually included software, the software that I used to discover these shapes, to explore them. You can do it yourself. Yeah. And I think that's cool, because most of us can't do that with the physical universe because we don't have access to Hubble. Right. Fortunately we get to enjoy the images because it's paid for by our tax dollars, so we get to enjoy the results. But with the Mandelbrot set, that's a universe that you can explore for yourself. It is infinite, which means you can spend the rest of your life exploring it, and you still won't have even scratched the surface. That's incredible. And yet you can do it from the comfort of your own computer.
That is just absolutely incredible. And so, and this brings up a why question about God. We have lots of why questions about God that may have no answers, but I've always wondered, like with the discovery of the immensity of our universe, with galaxies and all this stuff, and these discoveries that have been forthcoming in the last century or so, including the Mandelbrot set very recently. Why I wonder, and I'm not saying this is a question we can answer, but just kind of thinking about it, because obviously you conclude that this is all reflective of the mind of our Creator, of God, of the Logos, of Christ. And why does God wait so many generations to show us these things? Why did He keep them veiled from most of church history, that we get to see these things that our ancients did not? What do you think's going on there?
Well, a couple things. First of all, God's glory has always been known to all people, because anybody can go outside under the night sky and look up, and they can see the majesty
Absolutely.
of the Lord in His creation.
Yes.
And so it's God's glory has always been accessible to people in terms of being able to enjoy what God has made. And in some sense, in terms of the beauty of the night sky, the Milky Way, and so on, in some sense, the average person has less access to that today, in the sense that light pollution is such a big problem.
Right.
You know, most people live in a city or near a city, and you go outside and you see kind of a glow, and it's just from the lights from the city.
Right.
Whereas in the past, I'm a little bit envious of my ancestors who could just go outside any night and look up, and it's just perfectly black, and you could see the Milky Way and all that.
Yeah.
I have to drive about 40 miles to get away from the light pollution of Colorado Springs, which isn't terrible, but it's there.
Yeah.
But I do feel very blessed that I live in a time where the Lord has allowed us to see far more than our ancestors have. And see, I would expect that to continue. I don't think we've come anywhere close to discovering all that there is.
Yeah.
There may be an infinite number of secrets in the universe that we haven't discovered yet. And so 1,000 years from now, if the Lord tarries, we may be talking about things that we just haven't even conceived of yet.
Right.
So why today? I think this is my opinion. This is my speculation.
Sure.
I think it's a reward for the obedience, faithfulness of our ancestors, because the scientific method comes out of Christian thinking. The fact that God upholds the universe in a consistent fashion for our benefit, and therefore we can do something. We can probe the universe. God made our senses to be basically reliable. He gave us rationality so we can look at the various options and choose the best. God made the universe. God made us in His image, and so we have the capacity to explore the universe and understand it. And indeed, the Renaissance and many of the scientific discoveries came from Christian thinking, and most of the founding fathers of science were either Christians or at least had a great degree of respect for the Bible as the Word of God.
Absolutely.
And as a result of that, technology has exploded. Yeah. And so I think it's a reward or a result of Christian thinking, and it'll be interesting to see as our nation increasingly turns away from God. At some point, those blessings will be withdrawn.
Yeah, so it's kind of frightening the direction that we're headed as a nation. Given the history of nations, our future is not looking, I hate to be pessimistic, but when you get soft on the inside, it makes it easy for people on the outside to come in and take over. Whole nother discussion there, of course, but you bring up this issue of what I see again and again inherently problematic for naturalism and materialism is this idea of an intelligible cosmos that secular science is borrowing. In the language of, I say, Frank Turek, atheists are stealing the intelligibility concept from God without being able to explain why the universe is intelligent. And it was, as you say, the founders of Christianity who assume the universe would be intelligible and thus worthy of investigation because God made it to be intelligible and to be understood, as Romans 1 says, and Psalm 111:2. Great are the works of the Lord; they are studied by all who delight in them. That's on the Cavendish Laboratory over the door of the lab that James Clerk Maxwell put there when he was studying light. And so here we are, as you say, a reward, a benefit of the faithful Christians that came before who were exploring nature and giving us a robust picture of God's design. Okay, so enough theory. Let's jump into the more of the specific beauty of this thing. We found little Mandelblots, tiny little Mandelbot babies. I think that's really cute. Let's go into one of the things I love, these little valleys between the circles. When you zoom in on a valley, let's go to the elephants because they're on the outside there. They're in that little heart part, and let's talk a little bit about the Valley of the Elephants. Why this name and what's going on here?
Mathematicians love to give names to the various sections of the Mandelbrot set, and I think that's fine. That's an aspect of human nature. We like to classify things.
Right.
And indeed, when you zoom in on a cusp, anywhere where one part of the Mandelbrot connects to another, where there's this deep valley, trench, cusp, whatever you want to call it, there's almost always a lot of tremendous beauty there. So you have the Valley of the Seahorses, Valley of the Double Spirals, and Valley of the Elephants, which is the one that's on the right side of the main cardioid there. When you zoom in on that, you'll see these shapes, and lo and behold, it looks like little elephants marching along one after the other.
Yeah.
In fact, you'll find a series of perfect circles, and each circle has one elephant sitting on top of the circle, marching along.
Yeah.
And then if you do there's a mirror image of it, like elephants clinging to the roof upside down, going along the top. And so if you zoom in on one of these elephants, you'll find that it has this really curly trunk that curls up, and the farther into the cusp you go, the curlier the trunk gets.
Yeah,
so
there's an infinite curl to the trunk. It's a singular spiral, correct, as opposed to a double spiral, which you go down into the elephants.
Right.
And again, to reemphasize, all we're looking at here are graphed pictorials of solutions to the Mandelbrot with various numbers being plugged in. You mentioned chaos at the beginning, and I'd like to clear that up a little bit in relation to, as we're looking at the Valley of the Elephants here. When you hear that theory, I mean, I hear my skeptic friends will say this, that a butterfly's wing, a little breeze, and a tsunami, however many years or however much time passes, a butterfly can cause a tsunami, that kind of thing. But here in mathematics, when we're talking about chaos, what we see is what you said earlier, and I think this is an important point. We're adding very specific integers into this equation, and we're getting very specific and controlled designs. This isn't just kindergarten scrawl, right? We're just not looking at little scrawls from a crayon. This is a controlled environment where the chaos is really just a matter of the design changing, not that design and intelligibility goes out the window. Correct?
Yeah. Chaos is not it's not anti-design. It's just that chaos in a mathematical sense refers to something that when you have a very small change in the starting point, it results in an enormous change in the outcome. For example, the point positive 1/4 is the last point that belongs to the Mandelbrot set on the real number line. So if you add 0.0, so basically, if you take 1/4 and you run it through the formula, I think it does belong. I think it's the limit that does belong. You run it through the formula, z will stay bound. It'll stay small.
Okay.
But if you take 1/4 plus 0.00000001 and run it through the formula, z will not stay bound. It will eventually get really, really big.
Wow.
And so the fact that you have one point that generates a sequence of z that stays small, and another point right next to it for which the sequence of z gets big, that's an example of chaos, because you've changed the initial condition by just a tiny amount, and it results in a huge change in the outcome. And that's why it wasn't really until the 1980s that we could explore these things, because it required you to be able to run a number through the formula many, many times. Now, mathematicians were aware of chaos before that, and so you can talk about Julia sets and things like that that preceded the discovery of the Mandelbrot set. But in terms of being able to plot them and see the color shading, which demonstrates how quickly the point escapes, that wasn't done until the 1980s.
Okay, all right. So we've been to the Valley of the Elephants. We have this wonderful infinite spiraling of elephant trunks. We have another valley in this, the Valley of the Seahorses. Essentially, same thing going on. Why? Okay, so my question is, I'm watching this, and I'm looking and watching your videos, and I'm seeing this. The difference in the valleys, say the elephant shape and now the seahorse shape. This is just different variables? Why do we have such what's the difference in the elephant seahorse? What mathematically what's going on?
Well, they're different numbers you're putting in. You're looking at a different section of the map, and it so happens that one section of the map, the way it branches out, and I should explain this too, because when you see these images, you're going to see points that are very, very brightly colored, forming the shapes of the elephants and the seahorses and Seahorse Valley. And you might think, okay, because bright color means it's very close to being on the Mandelbrot set. Okay. So there should be a black point right next to it. Well, there is. It's just it's smaller than the ability of the printer to plot. So what you're really seeing in these shapes is the Mandelbrot set. Points that do belong form this very thin thread that wiggles around and branches and branches into branches and forms these incredible shapes. But the black thread itself is too thin to be plotted even.
Okay.
And so you're seeing sections that the actual bright points are points that almost belong to the Mandelbrot set. They're very, very close. And so that tells you that the shape, the perimeter of the Mandelbrot set branches out and branches into these complex structures. And depending on which number you're using, it'll either branch off and make like an elephant, or it'll branch off and make like a seahorse. Wow. I'm not sure anybody's been able to explain exactly why you get those shapes, but there they are.
That's fantastic. Now, so we have the Valley of the Seahorses, we have mini Mandelbrots, we have elephants. What other surprises, what other things delight you about this particular design, Jason?
In the Seahorse Valley, if you go to the other side of it, they give it a different name. It's called Double Spiral Valley. That's my favorite of all the sections of the Mandelbrot set. You get these gorgeous double spirals. Double spirals where you have two strands that wrap around each other, but never touch, except perhaps at the middle. So if you trace one strand, you'll see, yep, there's one in between it as well. And a lot of them look like spiral galaxies, which is, I think, cool. So, So as an astronomer, I appreciate that.
Absolutely. And so you mentioned astronomy. We talked about astronomy. You are a professional astronomer. I want to know, I'm dying to know as I'm reading your book, what insights does this give us? Or what insights does this give you for the universe? Because the Mandelbrot set is one equation, right? So I'm asking myself this as I'm reading this. I mean, this is just z squared plus c. Now, what kind of designs would be in other equations, Jason, and how would these be applicable to your field of study?
Yeah, well, that's one of the things we explore in the book. Is after we go through the major features of the Mandelbrot set, I ask the question, what happens if we change the equation? Yeah. And it turns out if you change c, like c divided by 2 or times 2 or plus a half or whatever, it doesn't really do too much. It'll either move the Mandelbrot set or rotate it or make it bigger or smaller. Oh, okay. But if you change the power of z, you get a totally different shape. And so I tried, instead of z squared, let's try z cubed. And you get a different shape. And it turns out that everything increases, which is interesting because we're increasing the power from 2 to 3. And so the main shape, instead of being a cardioid where you have a single cusp on the right side, you now have a nephroid, which has 2 cusps, one on the left, one on the right. Wow. And a nephroid is what happens when you take a circle half the size of another one and attach your pencil to one point and roll it around. Okay. You will now get 2 cusps, one on the left, one on the right. Wow. And it's perfect. It's a perfect nephroid. And the circles, which have no cusps in the Mandelbrot set, in this new set become cardioids, which have 1 cusp. That's so cool. Everything goes up by 1. That's so cool. And occasionally something will go up by more than 1. Like the mini Mandelbrots, those get multiplied by 4. So there are 4 minis in the new shape. Okay. And so you get the same kinds of properties, but everything goes up by 1. There are these little bow tie structures in the Mandelbrot set that look like 2 overlapping, 2 spirals that cross in the middle. And then in this new set, they grow an extra arm. So they got 3. They look like those little fidget spinners that serve for logical purpose. Yeah. They look a lot like that. So it's it's interesting. Everything goes up by 1. So you again have a new shape, and this is mind blowing to me because remember the original Mandelbrot set, infinite complexity. You can spend the rest of your life exploring that shape. You won't scratch the surface. Right. It's one formula. There's an infinite number of formulas. That's amazing. So that's fantastic. That is fantastic. And again, in my view as a Christian, that makes sense because God is the author of mathematics in the sense that his mind is responsible for it. And God is infinite, but he's not just infinite, he's infinitely infinite. Yeah. And that's wild too. And that's something that if you get into the more advanced math, you find that there are different types of infinities and some are bigger than others. And it's wild. It's really very interesting stuff.